Welcome to Precalculus, video lecture number 19 on complex zeros and the fundamental theorem of algebra. So the fundamental theorem of algebra tells us if a polynomial f of x has positive degrees and complex coefficients, then f of x has at least one complex zero. So complex includes real and imaginary numbers. So basically this is telling us you have a polynomial, it has a positive degree, complex coefficients, we don't need to stress too much about that. You have at least one zero or one root either in the real or imaginary numbers. Okay, so that's why we talk about them having at least one complex zero. And the complete factorization theorem for polynomials tells us if f is a polynomial of degree n, then there exist n complex numbers, C1 all the way up to Cn, such that you can write f completely factored as a, that's some coefficient, times x minus C1 times x minus C2, all the way up to x minus Cn. So each number, c sub k, is a zero of f of x. And this is exciting because now this tells us whatever the degree is of the polynomial, as long as we look in the entire plane of complex numbers, so not just real numbers, but we also include imaginary, then you're going to find that many zeros. So whatever n is, you'll have n many zeros. And you can write f factored with n many factors. Cool. So that means like if your polynomial has degree 100, you will have 100 complex roots. Don't worry, we won't do anything that crazy, but it's just what this is telling us. And lastly, the conjugate pairs theorem, which I touched on a little bit in the previous video when we were looking at Descartes' rule of signs. So basically, if f of x is a polynomial and you know that you have this complex root or zero, a plus bi, then also the conjugate, and we write that as r with a little bar on the top, then you know you're talking about the complex conjugate, which is a minus bi. That's also a real zero of f. So conjugate roots, conjugate zeros go everywhere in pairs, like little penguins, okay? And that's why when we did Descartes' rule of signs, when you were finding the max number of positive or negative solutions, you kept subtracting by multiples of 2 to allow for the fact that you might have pairs of complex solutions in there. Okay, so what we're going to do is go backwards right now. We're going to be given the zeros of a function and then write out what the function is. So they're saying find f of x, or find the polynomial, given that its zeros are -3 and 1 minus 7i. And they're telling me, P.S., f of x is degree 3. So if it's degree 3, it should have 3 zeros, correct? And they only gave me 2. Can you figure out what another one would be? Well, thank you, conjugate pairs theorem. I know for sure 1 plus 7i is also a zero of f of x. So now I can write f of x in factored form. So think back. Once we knew -3 was a zero, that was because x plus 3 was a factor, right? And then similarly, x minus, don't forget parentheses, 1 minus 7i has to be a factor, and x minus 1 plus 7i must also be a factor, since those are each the zeros. So here's 1 minus 7i, and then here is 1 plus 7i, and that's all three of them. And you can tell, all right, when we multiply it out, I'll end up with a degree 3 polynomial because I'm going to have x cubed as the highest term. All right, so let's hop to it. So we have x plus 3 times x minus 1 plus 7i times x minus 1 minus 7i. All right, this can be a foiling nightmare if you just go for it. Let me show you a slick technique, okay? And I'm just going to remind you of what happens anytime you multiply conjugate pairs. So when you have a plus b times a minus b, you just end up with a squared minus b squared, right? We should be pretty familiar with that. Well, what I want you to notice is that's exactly what we have going on right here. I have conjugate pairs, except a is x minus 1 and b is 7i. And then look, this is plus, this is minus, just like here, plus, minus. So I'm going to end up with a difference of squares. This will save you so much heartache. You're going to have a squared, this is a, b. A squared is x minus 1 squared minus b squared, 7i times 7i, that's 49i squared. Voila. And then just bring down that x plus 3. Don't forget about him. And from here, it should be smooth sailing. So we've got x plus 3 times, now x minus 1 squared, that's x squared, minus 2x plus 1. Remember, I squared is equal to negative 1. So that means negative 49i squared, that's negative 49 times negative 1, which is positive 49. So I have plus 49 here. All right, so far so good. So this is going to be x plus 3 times x squared minus 2x plus 50. We're almost there. We just got to FOIL this thing out. So let's see. X cubed minus 2x squared plus 50x. And then I'm going to distribute here and stack everything underneath. I think I've shown this before. So 3 times x squared, that's 3x squared, minus 6x plus 150. Combine your like terms, and you end up with x cubed plus x squared plus 44x plus 150. And box it. Lovely. Very, very lovely. Okay, let's look at another one just to make sure we have it under control. So here they're giving me the zeros. They're 0, 3i, and 4 plus I. And this time they're saying the polynomial or the function is degree 5. Well, they only give me 3 zeros. How rude. I'm missing 2. But remember, we have that conjugate pairs theorem, so I can figure out 2 more quite easily. If 3i is a 0, so is negative 3i. Think about it. 3i is 0 plus 3i, right? The real part is 0. So just switch the sign. And then if 4 plus I is a 0, so is 4 minus I. Fantastic. So now we can write out f of x. Do you remember if 0 is a 0, that means just plain old x is a factor. And then I'm going to have x minus 3i as a factor, x plus 3i, x minus, don't forget your parentheses, 4 plus I, x minus 4 minus I. Cool. So here, bring down the x. Now, these are conjugate pairs, so let's for sure multiply those by each other. That's going to give us x squared minus 9i squared. And then I need to distribute the negative over here, so I'm going to have x minus 4 minus I times x minus 4 plus I. Here's A, right here, and then here's B. Okay, so we're going to multiply it out. Let's do that first before we forget. You're going to end up with a squared minus b squared. So x minus 4 squared minus I squared. X squared minus 9i squared, that's going to become x squared plus 9, because remember I squared is negative 1 by definition. And then you still have that x hanging out there. Very nice. Good. So let's distribute this out. I'm going to have x cubed plus 9x. And then I'll multiply out x minus 4 quantity squared. So that'll be x squared minus 8x plus 16. And then negative I squared, that's negative negative 1. So that's going to be plus 1. And we're almost home free. So we've got x cubed plus 9x times x squared minus 8x plus 17. And now we just FOIL away. So distribute the x cubed. We will have x to the 5th. Yes, that's what we needed. Minus 8x to the 4th plus 17x cubed. Now I'll distribute the 9x. So 9x times x squared, that's 9x cubed minus 72x squared plus 9 times 17. You don't need a calculator, just do it like this. 9 times 10 is 90. 9 times 7 is 63. 90 plus 63, 153. Boom. So 153x. Okay, add it all together. And we are there. So I'm going to write f of x. You could write p of x. It's like a nice finishing touch. Is x to the 5th minus 8x to the 4th plus 26x cubed minus 72x squared plus 153x. Ooh, I love it. And you know what's pretty snazzy is you know what the zeros are because you built this function yourself. So if you ever feel like, playing teacher, making a worksheet, writing some polynomials and giving it to somebody and saying, hey, find the zeros, now you know how to write it and you'll have the answer key. Okay, the things math teachers did growing up for fun. Now we're going to go the other way. So basically we're going to have to find all of the zeros for a function, but they're helping us out. This is not as tricky as the last lesson where we had to just kind of dive in and start guessing. They're giving us a 0 and we have to find the remaining ones. All right, so here's the deal. This polynomial, this function is degree 3. They gave me 1 0, which is negative 5i. That means I need 2 more. So to get the other 2, I need to divide negative 5i into this polynomial so I can get the depressed or reduced degree equation, the one that's degree 2. You can do synthetic division with imaginary numbers. It's just a little wild. And so I do these problems a different way. Okay? So if I know negative 5i is a 0, I actually automatically know another 0 of this function, and that's positive 5i, since we have the conjugate pairs theorem. So since it's degree 3, and I already have 2, I only need 1 more. All right. Now, if negative 5i and 5i are zeros of this function, then that means I can write f of x as x plus 5i, x minus 5i, and then x minus c, where that's the missing 0 that I need. That's the one that I'm after. Well, how can I extract it? I want to divide f of x by x plus 5i times x minus 5i, because then I'll be left with x minus c. And so the way to do that, the best way, is using polynomial long division. So what we're going to do first is figure out what we're dividing by. So what is x plus 5i times x minus 5i? So x plus 5i times x minus 5i, that's going to be x squared minus 25i squared, which is x squared plus 25. So I'm going to divide f of x by x squared plus 25. There's 2 zeros sitting in here for my function. If I divide the function by x squared plus 25, the quotient will contain the remaining 0 that I'm after. So it's time to bust out the polynomial long division. We've got x squared plus, you need a placeholder, 0x plus 25. If you forgot polynomial long division, I'll link it up here I think I've linked it a bunch of times in the past, but good review. Into f of x, which is x cubed plus 3x squared plus 25x plus 75. Love it. So now we're going to divide x cubed by x squared. Just think to yourself, what do I need to multiply x squared by to make it x cubed? Just x. Then you distribute. So we'll have x cubed plus 0x squared plus 25x and subtract. The term on the furthest left should cancel out. If it doesn't, you messed up. And then here I have 3x squared plus 0x, and then bring down the 75. Okay, we can keep going. So what do I multiply x squared by to make it 3x squared? Why a 3, you say? Okay, so plus 3. And then now I'm going to distribute that 3 to the divisor. So we will have 3x squared plus 0x plus 75. Fantastic. Subtract, cancel, cancel. Let me ask you something. What if this remainder was not 0? Then that means you messed up. Because if you're dividing by something that contains zeros of f of x, you should not have a remainder. They should divide in evenly since they're factors of f of x. So that's a good check to make sure you're on the right track. If this is not 0, abort mission. Go back and figure out where your mistake happened. All right, can you see what the remaining 0 is? It's staring us right in the face. X plus 3, I'm going to set that equal to 0. Yay. So let's set x plus 3 equal to 0. That means x is equal to -3. So let's list out all the zeros in a solution set and then put f in factored form. They didn't ask us to be so fancy, but we like to overachieve. So in the solution set, I'm going to have -3 and then plus or minus 5i. This is the solution set. And then I could write f in factored form. So f of x would equal x plus 3, x plus 5i, and x minus 5i. All right, now you're ready for whatever they may ask. In this case, they only wanted the missing or remaining zeros. So the remaining ones were just positive 5i and -3. Okay, wasn't that fun? Let's try another one. So here we have 3x to the 4th plus 5x cubed plus 25x squared plus 45x minus 18. And they gave me that one of the zeros is positive 3i. Okay, so this polynomial is degree 4, which means it's going to have 4 zeros total. If 3i is a 0 by the conjugate pairs theorem, I know -3i also is. So that means I'm missing how many? I'm missing 2 more. So in order to get them, I'm going to divide f of x by x minus 3i and x plus 3i. And think about it. This is going to give me x squared minus 9i squared, which is x squared plus 9. If I divide f of x by x squared plus 9, my answer or my quotient is going to be degree 2. And that's exactly how many zeros I'm missing. So they're both going to be sitting in the quotient, in the result from my division problem. So here we go. I'm going to take x squared plus, I need a placeholder, 0x plus 9. And then divide that into f of x. So 3x to the 4th plus 5x cubed plus 25x squared plus 45x minus 18. Yay, so now just look at the leading terms. 3x to the 4th divided by x squared. Or think to yourself, what do I have to multiply x squared by to make it 3x to the 4th? It's 3x squared. Now you distribute that, 3x squared, and list the result underneath. So This is going to be 3x to the 4th plus 0x cubed plus 27x squared. And now we subtract. This cancels. And I have 5x cubed, and then be careful, minus 2x squared. Did you guys catch that negative distributing okay? Wonderful. And then now bring down the 45x, so plus 45x, and we can keep going. So I'm going to check, okay, 5x cubed divided by x squared. So I would need to multiply x squared by 5x. Now we distribute 5x to the divisor, list the result underneath. So 5x cubed plus 0x squared plus 45x. Subtract everybody. This cancels out here as we expected, right? If it didn't, we'd be in trouble. Something went wrong. And then I have minus 2x squared plus 0x. Bring down that negative 18. And we can go again, right? How do you know when to stop? If the degree here is less than the degree of the divisor, then that means you have your remainder. But we can keep going. We can keep going. So x squared into negative 2x squared, that's going to be negative 2. And then we have negative 2x squared plus 0x minus 18. Subtract this. And we have remainder 0, which we expected, right? Because I divided f of x by what I knew contained its factors, so it should go in evenly, no remainders. All right, where are the remaining two zeros sitting? They're in here, in 3x squared plus 5x minus 2. So let's extract them. So I'm going to set 3x squared plus 5x minus 2 equal to 0. Ooh, it factors, so we have 3x minus 1 times x plus 2 equals 0. And then setting each of the factors equal to 0, I get x equals 1/3 or x equals negative 2. My goodness, we got them all. Isn't it so satisfying? So here, let's put the solution set together. They gave us 3i. So we figured out, all right, we've got plus or minus 3i going on. And then also 1/3 and negative 2. How lovely. Let's write f in factored form. So f of x would equal, now notice, remember I mentioned last time, when one of your zeros is a fraction, right, the denominator's not 1 on that rational number, and notice the coefficients of f, they're all integers, then what you need to do is multiply by the denominator in front. So I'll put a 3 here. And also you could tell, ooh, that was going to be necessary because of this step here. Okay? That way, if you were to multiply everything out, you would get back f of x. So I have 3 times x plus 3i, x minus 3i, x minus 1/3, and x plus 2. That way, when you multiply it out, you get f of x, the original. So nice. These are quite a bit easier than the last lesson because they already give you a 0, so you have something to go off of. Okay, but that's not necessarily always the case. So we're going to conclude with one where we have to combine our methods for when we found real zeros of a polynomial. So last example, find all the complex zeros of f of x. They're giving us nothing to go off of. So we're going to bust out the rational zeros theorem. Okay. Notice here f is degree 3. So I know I need to find 3 zeros total. How am I going to start? I'm going to list all the possible p's over q's. You remember doing that? So I have plus or minus all of the factors of 85. My goodness, 85 has a lot of factors. 85, 17, 5, and 1 divided by all of the factors of 1. Okay, so remember, you just start guessing what might work and use synthetic division. So say, you could use Descartes' rule of signs if you feel like it. I'm not particularly in the mood, but it's up to you. Say we try -1, so we've got 1, 13, 57, 85. So let's see here. This is going to be 1, negative 1, 12, negative 12. This will be 45, negative 45. This isn't 0. All right, so you play around with it perhaps. And guess what works? Negative 5. Yes. So we have 1, 13, 57, 85. Bring down the 1. This is negative 5. This is 8. Negative 40. 17. Negative 85. Ding, ding, ding. So in the solution set goes negative 5 before we forget. Negative 5 works. Now, I need 2 more zeros still because this is degree 3. Where are they sitting? Right here in the depressed equation, the one that's degree 2. So 1 is the coefficient of x squared, 8 is the coefficient of x to the first, and 17 is my constant term. I'm going to set this equal to 0. Now, how can I squeeze out the other 2 zeros? This doesn't factor. So it's time to use that quadratic formula. Here we go. So x is going to equal opposite of b plus or minus square root. We have b squared minus 4ac all over 2. So this is negative 8 plus or minus square root. We have 64 minus 4 times 1 times 17, that's 68 over 2. All right, and let me help you clean this up. So we have negative 8 plus or minus 64 minus 68, that's negative 4. So I have square root, let's write a cute square root. Square root of negative 4 over 2. And what's the square root of negative 4? It's just 2i, right? So I'll just remind you, square root of negative 4, think of it as square root of negative 1 times 4. So you write that as square root of negative 1, square root of 4. That's I, that's 2. So I just think to myself, take the square root the way you normally would and slap an I on there, right? Then you get 2i. Okay, so negative 8 plus or minus 2i over 2. And then I can reduce, divide by 2. So this is negative 4 plus or minus I. There's my 2 other zeros. So I got all 3, didn't I? We're so good. So we've got negative 5 in the solution set and negative 4 plus or minus I. You can box that with pride. That was a job well done. Ooh. So sometimes you need to use the methods from the previous lesson. You could use Descartes' rule of signs as well if you wanted to help narrow down, what you should start guessing with for the synthetic division using the rational zeros theorem. Conjugate pairs theorem, you need long division, you need everything. That's how math works. I hope you enjoyed it. And that wraps up this unit. So moving on, we're going to do inverse functions, all sorts of other fun stuff. But that's all she wrote for this unit. Don't forget to subscribe, give this video a thumbs up, and stay tuned.